All right, welcome back to Applied Algebra and Trigonometry. We are going to finally dive into the subject you've been waiting for all semester, or at least I've been promising you all semester, complex numbers. There is one thing you must understand in order to understand complex numbers, and that is complex numbers give you the ability to deal with -1. In fact, some of you may know what this is equal to. The square root of -1 is equal to j. Some of you thought I, right? Some of you will also be using imaginary and complex numbers in dealing with electricity. And I'm talking about electricity, in which I often represents current. So to avoid confusion in this class, the square root of -1 does not equal I, it equals j. This also means that if we square both sides, we have the fact that -1 equals j squared. And now we start building upon this. Let's play around with the variable a. But let's say that a is positive, greater than 0, just to make things a little more clear as we're starting out here. So if we look at the square root of -a, given what we've already decided, how we're going to define the square root of -1, from our work with radicals, we know that the square root of -a can be rewritten the square root of -1 times the square root of a. And we know the square root of -1 is equal to j, so we can rewrite the square root of -a as j square root of a. And we can, didn't mean to move that. We can rewrite the square root of -a squared as the square root of -1 times the square root of a squared. And that will give us j times a, or ja. Or, the other way around, aj. Okay. Conventionally, the way we write our answers is, if there's a radical, it follows the j, as in the first case. J comes first, then the radical. If there is no radical, j follows whatever number it's associated with. You get used to it after a while. Okay, so let's look at some examples that actually involve numbers and not just letters. How about the square root of -5? That can be rewritten as the square root of -1 times the square root of 5, or j square root of 5. The square root of -16 can be rewritten the square root of -1 times the square root of 16. Okay, which is j times 4, or, wait a minute, there's no radical, so the j comes last. Since the j comes last, you could also recognize that the square root of -1/9 is the same as the square root of 1/9 times the square root of -1. And when you take the square root of 1/9, you get 1/3. The square root of -1 is j, and it's already in the right order. Either way it works. Okay, what about the square root of -0.04? That one looks a little more complicated, but you can work it out the same way. This is just the square root of 0.04 times the square root of -1, which is 0.2j. Wait a minute, how did I get that? Well, look at it this way. That is, if we read it using our place value, 0.04 is equal to 4 hundredths. So we have the square root of 4 hundredths times the square root of -1, which is, when we take the square root, 2/10 j, which can be rewritten that way. If you're not going to rewrite it that way, however, if you want to keep it as a fraction, you do have to simplify it. For those of you keeping track, that was 5 examples. Let me give you a 6th before we move on. What about the square root of negative 28? Well, that's equal to the square root of 4 times the square root of 7, because 4 times 7 is 28, times the square root of negative 1. Why did I pull the 4 out of there? Because I can take the square root of 4. And I can take the square root of negative 1, so maybe I should have put these in the other order. But that's j, and then I have the square root of 7. And that's my final answer. Be careful. The square root of a times the square root of b does equal the square root of ab, or the square root of ab equals the square root of a times the square root of b, if and only if a and b are not both negative. Okay, if they are both negative, you cannot use this formula. For example, okay? I'll put that warning right up there where you can see it. Okay, negative 25. Take the square root of negative 25, but square it. Okay? Let's see. If we do it this way, if we let that equal, okay, so I'm going up here. It's the square root of negative 25 squared. That means it's the square root of negative 25 times the square root of negative 25. That's what squared means. So the square root of negative 25 from what we've just learned is 5j times 5j, which is equal to 25j squared. But we know j squared is equal to negative 1, so we actually have here negative 25. Okay? On the other hand, if we try to do it this way, okay, and we combine them, okay, as negative 25 times negative 25, so we have the negative 25 squared, right? And we're taking the square root of it. We would get 625 underneath that radical, and that is equal to 25. So be very careful. Another example. See, those are two different values for the same thing. Which one's right? Okay, this one is right. Okay, and this one, although I like red, I'm going to use it as the warning color. Wrong. We must say it does not equal this one. Likewise, negative, or the square root of negative 5 rather, times the square root of negative 20 does not equal the square root of negative 5 times the square root of negative 20. You cannot pull them under there together and get the right answer, because if you do that, you're going to have the square root of 100 when you multiply those two, and the square root of 100 you're going to say is 10. See, our radicals are already there. We're not considering positive and negative cases. We're starting with the radical, so we're giving the positive answer. Except for on the other side, if we evaluate that, the square root of negative 5 is j square root of 5. And the square root of negative 20 is 2j square root of 5, because just as an aside here, in fact, over on the right side, you'll see how I turn negative square root of 20 into 2j square root of 5. But anyways, back to what we're doing here. This will give us 2j squared square root of 5 squared, which is really equal to 2j squared times 5, or 2 times 5 is 10, but j squared is a negative 1. And as you can see here, negative 10 does not equal positive 10. Okay? The right-hand side is the incorrect way to do it. If you're asked to multiply radicals that have negatives inside, evaluate them first. Find the j's, express them as imaginary numbers, then multiply them, and continue evaluating. All right, time for lots of examples, because if this is the first time you've encountered imaginary numbers, it will take lots of examples to really cement the fact that these aren't imaginary. They actually have meaning. You can actually work with them. And those of you who are going into anything to do with electricity will find them extremely useful. It's a case where math discovered a theory that proved useful in the real world. It's done that a lot, actually. Here's another example. I will call this, let's start using letters. This is example A. Okay? Square root of negative 125, square root of, 121. Square root of 121 is 11. Square root of negative 1 is j, 11j. Okay, example B. Negative square root of negative 49. All right, this is where you have to be really careful. When you are evaluating this, do not drop that first negative. You're going to have a negative of whatever the square root of negative 49 is. Well, the square root of negative 49 is 7j, so your answer is negative 7j. Example C. All right, the negative square root of negative 100th. Okay, so that will be the negative. Okay, we're going to have a negative coming out of there, so we're going to have a j in here. But what is the square root of 100th? It is 1/10. Write it as a fraction if you need to see that. And j. Okay, for example D, how about 3 times the square root of negative 48? What do? We have still the 3 out there. And wow, what about what's underneath there? Let's factor it this time. Is there a perfect square within 48? Yes, it's called 16. And 3 times 16 will give you 48. So there's 48, not completely factored, not factored to the primes, but factored until I found the biggest square root I could inside of there. All right, so now I can continue evaluating. 3j times 4 times the square root of 3. Okay, I have actually here 3 times j times 4, so that will give me 12j followed by the radical. All right, and E, example E, the square root of negative 2 pi. You knew I couldn't leave pi out of it for very long. Okay, we have negative 1 times 2 underneath there, so they're each under their separate square root. Then we have the square root of, now watch this, pi to the 4th times the square root of pi. Why did I do it that way? Square root of 1 is, negative 1 is j. Square root of 2, I can't pull anything out of there. Square root of pi to the 4th is pi squared, because pi squared times pi squared gives me pi to the 4th. I have left under the radical. I couldn't pull anything out of here. I couldn't pull anything out of here. So those are left under the radical. Okay? Now, whoops, my j's in the wrong place. Pi comes before j. The radical comes after j. All right? Let's do one more before I have another important point I want to make. Okay, negative square root of negative 9/5 equals. We have the negative out there. Then we have a negative 1, and it's multiplied by the square root of 9/5. Okay, and you know what? That's looking kind of strange here. Let's go ahead and make this a negative j, and then deal with everything else. The square root of 9/5 is the same thing as the square root of 9 over the square root of 5. And the reason I'm breaking it up that way is, look, we have negative j. I can evaluate what's on top there. Square root of 9 is 3. But I have a radical in the denominator that I cannot get rid of yet. You have a technique for getting rid of that. It's called rationalizing the denominator. If we multiply both the numerator and the denominator by the square root of 5, we will get, or that will equal, negative j times 3 square root of 5 over 5, which kind of looks nicer if we write it negative 3/5 times j times the square root of 5. Yes, you have to rationalize the denominator if necessary. Yes, you have to remember all the algebra we've learned all semester. Yes, no, just the answer is yes, you do have to. Whatever the question was, it's yes. But you know me better than that. Go ahead and ask questions either by email or during our Collaborate sessions. All right. But also note, if you are given something like this in the original problem where you have a radical and you have a negative and it is squared clearly under the radical, and whoever wrote this problem wants you to do it this way, then go ahead and multiply negative 15 times negative 15 under the radical. That is a perfectly fine way to do it. The indication here is that that is what the person is trying to communicate, right? However, if you have this where it is clearly squared outside of the radical, that is saying it's the square root of negative 15 times the square root of negative 15. So this you must evaluate first. Each of the negative radicals, and then multiply. Another example, if you are given this with both of the negatives already under the same radical, then in this case, you would multiply them first and take the positive square root. If those numbers, those negative numbers, were originally under their own radicals, then before you multiply them, evaluate them, and then multiply. So then you have 12j squared, or negative 12. Take a look at these examples. It all depends upon what the person writing the problem, or you if you're writing it, intends to communicate. We have only begun to scratch the surface of imaginary numbers with this video. Therefore, there is a second video for this lesson. Look for it.